Hello everyone, my name is Jiang from Institute of Information Engineering, Chinese Academy of Sciences. Today, I will give a brief introduction about our work, Chameleon, towards building least privileged TE via functionality-based resource regrouping. TE allows applications to execute sensitive data in an isolated, trusted environment. It used hardware-assisted technology trust zone to enforce protection. Normal applications run on the rich execution environment. Basically, that's Android. This environment opens to the malware and jailbreaking. However, the sensitive assets are isolated in the TE, such as the fingerprint recognition, secure payment. All the components in TE is assumed to be trustworthy. However, as trust zone adoption grows and customization needs increase, TA and TOS implements has become more flexible and more complex, leading to a large attack surface for the TE. The OPTE OS code base has grown from 55K to 268K lines of code over time, which increase the likelihood of vulnerabilities, such as this table shows the TE system vulnerabilities report. Existing solutions improved security by running a full TOS for each TA, but it's too heavy for the resource-limited mobile devices. So the key question is, how can we enhance security while keeping the system lightweight? We started by analyzing where vulnerabilities shows up in the TE components. First, we gathered CVE reports using keywords like trust zone, trusted OS, trusted applications, and filter for those marked high or critical in the CVSS scoring. Our analysis shows that the most vulnerable parts are the TA, the libraries used, and TOS services, together accounting for 79.71% of the report CVEs. It shows that this complements needs more careful design when improving system security. Next, we look at all the public available TAs on the GitHub. We extract their functions and count how many TOS services APIs they actually use. It turns that most TA only need a small subset of the available interfaces. But the problem is current system expose all the TOS services to TA without any restrictions. This creates a serious risk. A compromised TA could misuse these services to take over the whole system. Then the whole system is not secure anymore. Based on these findings, we proposed a least privileged-based decoupling and isolation of TOS, providing an independent TA entity for each TA to execute within customized TOS services. The original TOS is partitioned into a manage unit and sets of capsule. Capsule provides customized constraint TOS functionalities for TA, following the principle of least privilege. The T-visor is a tiny TCB in year 3. Managing this TA entity and enforce the isolation. In Chameleon, we focus on mitigating the attacks that exploit the internal integration within the TE. We look at 3 main threats: cross-TA entity compromise, and malicious TA installation, and denial of service attack. This often happens because TA overuse the TOS services or share kernel resources. We don't cover attack from outside the TE, like RE to TA attack, cryptographic flaws, or physical side channels. This requires a secure development practice or hardware support, which is beyond the Chameleon's software-based scope. We assume that the ARM-trusted firmware in year 3 is secure, since it's the root of trust for T setup. We face 2 main challenges in our design. First, how to reorganize the TOS resources into capsules so that each TA gets just what it needs, no more, no less, without duplicate the code or breaking things. Second, how do we make sure each TA only has limited privilege? It means setting strict control so one TA cannot mess with others or gain extra privilege. First, to regroup TOS resources, we first decouple the TOS into components like the TE agent and the memory management. These components are then recognized into either capsules or the managed unit. The capsule include models specific to the TA's functionality, and we follow the least privilege principle to exclude unnecessary services and reduce the attack surface. The managed unit hold the functionalities that are independent of the TA execution, such as loading and scheduling and stay outside the TA's runtime environment. For the second challenge, to restrict the TA entity privilege, we enforce fine-grained access control over memory. During the TA load stage, we split the original text segment into multiple service segments and selectively mapped only the needed ones into the TA entity. Sensitive operations like memory mapping or context switching are trapped into the T-visor for validation. Ensure each TA entity can only access its own resources. Besides the memory control, regulating instruction execution is also critical. For example, in instruction like TTBR rise are alter the address space and break the isolation. To prevent this, we either hide the high-risk instruction from TA entities or trapped them into the divisor for validation before allowing execution. We implement a prototype of Chameleon on Linaro's OPTE. Our system is developed on the Heqing 960 development board. The implementation requires about 2,900 lines of code changed to the OPTE source. In our prototype, we provide a method to partition TOS service. First, we analyze the TA's functionality by extracting the API core. And second, we classify these TAs into functional sets like crypto, storage, or DRM. Third, we map these APIs to the underlying TOS services they depend on. Finally, we use the Venn diagram to identify shared and unique services and group them into lib services for efficient partition. Our system significantly reduced the memory overhead compared to existing entire TA instance method. For example, in RedZone, each TE instance requires 32 MB of memory, but our system adds only a minimal memory overhead, less than 1 MB. For security evaluation, Chameleon reduced the attack surface of the TOS services by an average of 49%. Meanwhile, Chameleon can migrate 88.41% of trust zone TE-related CVEs. OPTEX text is a suite of regression tests provided by OPTE to verify the correct implementation of the TOS and the related applications. The suite is also has performance benchmark related to the cryptographic and the storage operations. Results show that our system Chameleon introduced minimal overhead compared to the original system, and the boot overhead is under half a second, and the switching between contexts takes less than 1 CPU cycle. We also evaluate Chameleon's performance in 5 real-world TA. The results show that the average performance overhead is around 8%. In summary, we make following contributions. We conduct a comprehensive analysis of vulnerabilities in trust zone-existed TE. Based on this, we propose a novel customized TOS design called Chameleon. We also implement Chameleon as an open source prototype on OPTE, which improves system security while keeping the design lightweight. This is the end of my presentation. Thank you for listening.
We have time for a couple of questions. Hello, Miles from UC Irvine. Thank you for the interesting talk. So one question I have is, it looks like you're specifically focusing on the trust zone architecture for this work. So I wonder for the latest ARM v9 CCA, which has the Realm VM as a new type of TE. So compared to that, how would you say what's the contribution of your work? Because it seems that they're saying that, well, a lot of trusted applications, TAs should be able to be ported to Realm VMs which can significantly lower the TCB, right? Because real VMs, they're separated, they're isolated from each other.
Sorry, do you mean that how our design implemented to the CCA?
No, I wonder how does your work would be compared with the latest ARM v9 standard, which has ARM CCA, and inside of it there is this new type of TE called Realm, right? Realm VM. Have you?
Yeah. The RIM, but the CCA is, I think, is not used so widely now.
Yeah, it's not used because it just got introduced like a year or two ago, but it is going to be widely available as people start adopting ARM v9, right? So how would your works be contributing to it? Because people might start leaning towards ARM Realm than Trustzone.
Yeah, but most of our mobile, such as mobile device, the CCA is not deployed.
Okay.
Okay. Yeah.
Okay.
And the least privilege principle is also can be used to the CCA in the future, I think.
Okay, but Realm is only supposed to run one application per VM, which is then isolated from each other.
Yeah. The CCA provides Realm to execute the one, for example, one TA, but in the Trustzone, it only has one trusted execution environment. So we focused on the Trustzone because the TE is not secure. Yeah.
Okay.
So.
Got it. Yeah. Sure. Yeah, it's definitely important to still solve the Trustzone problem. It's super blotted already. Yeah, I agree. Yeah. Thank you very much.
Okay, thank you.
I also have a question. I like the fact that you're doing this segregation based on the resource types. And I imagine there will be a lot of communication between the trusted applications and with the untrusted OS. And this communication it sounds like another attack surface. If more than two trusted applications may be colluding, is it in your threat model?
Do you mean that the communication between the RE and the TE?
Both. For example, there may be a TE is malicious, and they collude with the untrusted OS or with another TEs, and then they can have more like a combined privilege from those two components.
In our threat model, we focus on the internal vulnerabilities. And in our another work, we focus on the channel between the RE and the TE.
I see.
Yeah.
Got it. Thank you.
Okay.
Let's give the speaker another round of applause.